All right. I want to go through the pH of aluminum hydroxide. All right. So your aluminum hydroxide has a KSP value of 4.6 times 10 to the minus 33. Minus 33 is extremely small. All right. So the initial, when we're in water, normally everything initial is 0. Well, in water, there's no aluminum plus 3. However, water has a Kw of 1 times 10 to the minus 14, and that is the concentration of your H plus times your concentration of your OH minus. And so each of those has a concentration of 1 times 10 to the minus 7. And so our OH minus concentration is 1 times 10 to the minus 7. All right, so you cannot have a 0, and so at equilibrium, you have your plus S and your plus 3S for your OH minus. So at equilibrium, we have our solubility, S for the aluminum plus 3, and 1 times 10 to the minus 7 plus 3S. And since our K value is so small, minus 33, we are going to neglect our plus 3S, and then we'll check to see if that is going to give us the same answer when we do our successive approximations. So we plug in our numbers, KSP, 4.6 times 10 minus 33, aluminum plus 3, at equilibrium is S, and the OH minus is 1 times 10 to the minus 7 plus 3S. We are going to neglect our plus 3S because we know S is small because of this very small K value. So when you do that, you solve for S, S1, the first time we solve for it, 4.6 times 10 to the minus 12. All right, and so I see the minus 12, and I know it's not going to change, but because when you have minus 4.6 times 10 to the minus 12, now when you multiply it by 3, now it's minus 11. When you add a minus 7 to a minus 11, it's not going to change that number. So I left all the sig figs. When you take, when you put that in, you of course get the same answer again, 4.6 times 10 to the minus 12. So when you want to get your OH minus concentration, you take your 1 times 10 to the minus 7 and add 3 times your 4.6 times 10 to the minus 12. And that is 1.000138 times 10 to the minus 7. So barely higher than 10 to the minus 7. And when you take the negative log of that, you get a POH of 7 and a pH of 7. All right, and so it did not change. This K value is so small that the hydroxide that came from the aluminum hydroxide is such a tiny amount that it did not change the pH. The pH is still 7.00. Now, if you go out enough sig figs, your pH would have been, so if you go out enough sig figs, your pH would have been 7 point and then 4 zeros and then a 6. All right, so again, the pH has to be above 7, and it is above 7 if you go out to the 5th decimal, but to 2 decimals, it didn't change. So, and that's how we report all of our pHs, to do 2 decimals. And so the pH is above 7, but it's barely above 7, and it's so far out in sig figs that it is not included. And so the pH to the 2 decimals did not change from pure water. All right, and so again, these K values, some of them are extremely small and will give very, very little concentration for your ions. Now, your aluminum plus 3, if we wanted that concentration, then that is the 4.6 times 10 to the minus 12 molar. So that is your Al plus 3. Your OH minus concentration is the exact same, the 2 sig figs, the exact same as it was in pure water, 1.0 times 10 to the minus 7. All right, so that is the KSP. Today we're going to do the KF. All right, and so we are going to make a complex ion. All right, so when we make a complex ion, we are going to have a cation, a metal cation, and we're going to have a Lewis base, and they are going to combine to form a complex ion. All right, and so they have an ion, and remember that all ions are aqueous, and so they are soluble. They will be a part of our K value. And so the most common, the one we're going to deal with today, a very common one, is your Ag plus reacting with two NH3s. Now, when you draw the Lewis structure of NH3, you see that it has an electron pair. All right, and so that means that it can be a Lewis base. A Lewis base is an electron pair donor. In order to be an electron pair donor, you have to have an electron pair. All right, so your Cn minus, when you draw the Lewis structure of that, it has two electron pairs, but since the negative is on the C, that is going to give your Lewis base to two electrons from the carbon, your OH minus. All right, so you're going to have your OH minus, and it's going to have an electron pair to donate to a metal, whether it's the Ag plus, any metal ion, it doesn't matter. You can just put metal, stick with Ag plus. So the ligands that we are, once the Lewis base attaches to the metal, in this case, we're going to have two of our NH3s attached. We get an Ag NH3 sub 2 and a plus. All right, and so we then call them ligands. So here are NH3, these are ligands, also pronounced ligand. All right, here it is a Lewis base. So the NH3 on the reactant side is a Lewis base. It's an electron pair donor. Your Ag plus is a Lewis acid. It is the electron pair acceptor. So electron pair acceptor and electron pair donor. So anytime we are doing the formation of a complex ion, we are doing a Lewis acid, Lewis base reaction. Your metal is always going to be the Lewis acid. It is going to accept the electron pair from the base. Now, in order to be a Lewis base, again, you have to have an electron pair. Water would be another possible ligand because the bent shape of water, and you have your two electron pairs. So as long as you have an electron pair, you can be a Lewis base. If you have a BH3 and you draw the Lewis structure of BH3, this is the Lewis structure of BH3. There is no electron pair. If you do not have an electron pair, it cannot be a Lewis base. All right, and so if it can't be a Lewis base, then it cannot be a ligand. All right. So in order to be a Lewis base, you have to have an electron pair. Once you have then connected to the metal, you are then called a ligand. All right, and when we do the K value for this, this is going to be called a KF, where F is the formation of a complex ion. And so what's different about this is your KF values are always large numbers. So this will be the first K value that we have that is going to be a large number. So when we have this and we have our Kf, that is the concentration of your products. Again, that's aqueous. It's got a charge. All right, so it goes into the Kf. That's your Ag NH3 sub 2 plus divided by your Ag plus and your NH3. Now you have to be very careful because a lot of these have coefficients. All right, and so when you have the coefficient of 2 on your NH3, make sure you raise the concentration of your NH3 to that coefficient. All right, and so again, that is the same as a Kc. All right, so Kf is Kc. It is just being specific. This is the equilibrium constant for the formation of a complex ion. And then also Kf, always large. All right, which means that when you have an initial concentration, that the reaction is going to go completely to the right until something on the left is 0. So when we had the very small value, something on the right had to be 0. When you have a very large value, something on the left has to be 0. All right, and so one or both of the reactants must be 0. If not, you need to get a new initial. All right, and so it's going to go until one of those is 0. Once one or both of them are 0, then go to equilibrium. So at equilibrium, one of them is going to go to 0, but it's not going to be 0. It's going to be some small value. So we go to equilibrium to calculate the small value for that concentration. Oh, okay. If you prefer to work with small numbers, what you're going to have to do is reverse the reaction. So if you reverse this reaction and you have your Ag NH3 sub 2 plus, that goes to Ag plus and to NH3. Now your K value is called a Kd, and that's equal to 1 over the Kf. And since all Kf values are large and you divide by a large number, you get a small number. All your Kd values are very small. So D stands for dissociation of complex ion. And all of these are small. So if all your Kf's are large and you divide by a large number, then you're always going to have a small value for your Kd. All right, so our Kas, our Kbs, our Kws, our KSPs, all of those numbers were very small numbers. If you want to stick with the small numbers, you will have to reverse all the reactions and take 1 over the Kf in order to get the Kd. That is not how I will do it. I am going to work as written as a Kf, but I will show you that the book does work out the same problem as a KD, and you will get exactly the same answer. So whichever you prefer, you can do. All right, so on table 17.2, I said that all the Kf values are large, and here is the list. And so you got 10 to the 18th, 10 to the 7th, 10 to the 13th. All of those are large numbers, which means they favor the products, which means that an initial on the left has to be 0 before you can reach an equilibrium. If they are not zeros, then you have to go until one of them is 0, and then you reach your equilibrium. All right. So here is an example using Kf. what is the concentration of Ag plus in 0.01 molar AgNO3? That is also 1 molar NH3. And then the Kf for AgNH3 sub 2 plus is 1.7 times 10 to the 7th. All right, so we can write that Kf again, and that is our Ag plus 2 NH3 is in equilibrium with Ag NH3 sub 2 plus, which has a Kf value of 1.7 times 10 to the 7th. All right, and so we see that it says that it's in 1 molar NH3, and so we have an initial. That's 1 molar of NH3. It also says that we have 0.010 molar AgNO3. All right, you need to remember from chapter 4 that all nitrates are soluble. And so your AgNO3 doesn't have equilibrium, it has a single arrow. It is soluble, 100% ionized. And so you have your Ag plus and your NO3 minus. Again, that all nitrates are soluble. And so you have your 0.010 molar. All right, and we know that its final concentration is 0. It completely goes to the right. And so you get your minus X, you get your plus X, you get your plus X. And so you see that your Ag plus is 0.010 molar, your NO3 minus is 0.010 molar. And so when you're writing your initial concentration of Ag plus, it comes from the soluble AgNO3 of 0.010 molar. And we did not add any of our complex ion. And the Kf value is very large. So again, if we do not have a 0 on the left side, this thing goes completely to the right until one or both of my reactants are 0. And so we have to go to a new initial. And so we see that we have a very small concentration of Ag plus that is going to 0. And so we subtracted our 0.010 molar. And now this is 2 times that. We subtracted 0.020 molar. And this is adding 0.010 molar. And so our new initial is that is now 0. This is 0.98 molar. And this is 0.010 molar. So now we have a 0 on the left side. Our K value is large. It went completely to the right until something on the left was 0. Now, once we have something on the left is 0, now we can go to change in equilibrium. Until something on the left is 0, we cannot go to change and equilibrium. All right, and so the change, you can't have a 0. So we have to get some amount that we can call X. So that means that the reaction has to go to the left until we get some non-zero number for our Ag plus. So we have to lose some amount X here, we have to gain some amount 2X here, and we have to gain X here. All right, so the rule did not change for equilibrium. When you have an initial concentration that is not 0 for a reactant, and you have an initial concentration for a product that is not 0, your initial and your equilibrium will always be the same. You will neglect these numbers. You do not have to check them. Whenever you have a starting concentration of a reactant and a product, then that is also going to be its equilibrium concentration. So 0.98 molar is the equilibrium concentration of NH3. 0.010 molar is the equilibrium concentration of the AgNO3 sub 2 plus, and X is what we are solving for, is our equilibrium concentration of Ag plus. All right, and so we plug in our Kf, which is 1.7 times 10 to the 7th. That is equal to our AgNH3 sub 2 plus, that is our 0.010 molar, over Ag plus, which is X, and NH3 squared. So the reason why people miss this is because they don't square it. So 0.98 quantity squared. And so a good thing to always do is to write the expression Ag NH3 sub 2 plus concentration over Ag plus. I still have people write this and then they still don't square it, but it will help. But the reason why you would want to write this before you plug in the numbers is to hopefully not forget to square the NH3. All right, so to solve this, we multiply both sides by X. All right, we multiply both sides by X in order to have X in the numerator, cancel the X in the denominator. Then we divide both sides by 1.7 times 10 to the 7th. We divide both sides by 1.7 times 10 to the 7th. And now we have our answer for X. So 0.01 divided by 0.98 squared. And also divided by the 1.7 times 10 to the 7th. And that gives us 6.1 times 10 to the minus 10. All right, and so X is the concentration of Ag plus, and that was the question. What is the concentration of Ag plus? And so your Ag plus concentration is 6.1 times 10 to the minus 10 molar. All right, so now we're going to go through how the book solves the problem, and the book solves the problem by doing the reverse of the Kf. All right, so instead of forming the complex ion, they are dissociating the complex ion. And so the K value for this is 1 over the Kf, which is Kd. All right, and so when you take your 1.7 times 10 to the 7th and you invert it, you get 5.9 times 10 to the minus 8. All right, and so your initial was 1 molar and 0.010 molar and 0 here. All right, and so when you have a small number, the reaction is going to go to the left until something on the right is 0. All right, so the same way we did Ka and Kb. All right, so if you prefer this way, you can do it this way. I will always write Kf as Kf to do my problems, but the book likes to do it as Kd. It doesn't matter. It gives you the same answer. All right. And so when you have a very small K value, then something on the right has to be 0. And so we see that the Ag plus is much smaller, so minus the 0.010. And now don't forget the coefficient of 2, so minus 0.020 molar and plus the 0.010 molar. And so now you have your new initial of your 0.010 molar of your complex ion, 0 for your Ag plus, and 0.98 molar for your NH3. Again, at equilibrium, you cannot have a 0. And so the reaction has to go to form something here, so it's going to the right. All right, and again, when you have a starting concentration of a reactant and a starting concentration of a product, the initial and the equilibrium will be the same number. So you will neglect the minus x, you will neglect the plus 2x. You do not have to change it. When you have a starting, check it. When you have a starting concentration of a reactant and a product, you neglect the plus and the minus x, and it is not required to check it. It never will change the x value. All right, and so again, now we're going to solve for x. So this time our equation is KD. So we have 5.9 times 10 to the minus 8 is equal to X times 0.98 squared, don't forget to still square it, divided by the 0.01. And when you solve for X, you will get exactly the same answer, 6.1 times 10 to the minus 10. And so your Ag plus is exactly the same as we did it before. 6.1 times 10 to the minus 10 molar. So it doesn't matter if you want to do it as a KD or if you want to do it as a KF, you will get exactly the same answer. Since it gives me the KF, I will always write the reaction as a KF and leave it as a large number. But you can work the problem the other way to get the exact same answer. And so they go through the whole thing and they get the 6.1 times 10 to the minus 10 for the Ag plus. All right. Zinc hydroxide. Zinc hydroxide is an interesting compound. All right. It is an amphoteric hydroxide, which means it reacts with acid and it reacts with base. All right. So when you have a hydroxide, you expect that to react with an acid. Acid plus base gives salt and water. All right. But with our zinc hydroxide, it also reacts with the base, OH minus. And so the OH minus is just a Lewis base that does a Lewis acid Lewis base reaction. And those OH minuses become ligands. And now we have our complex ion. All right, so this is a very interesting reaction for your zinc hydroxide. It reacts with both acid and base. That is called an amphoteric hydroxide. All right. Anytime you have a question about precipitate, will silver chloride precipitate? You always think KSP. So anytime I see precipitate, I know I'm doing a KSP reaction. All right, so all sodiums are soluble and all nitrates are soluble. So you need to recognize the question as this is a 0.010 molar Ag plus. We already did that. That is completely soluble, goes completely to Ag plus and NO3 minus. Same with the NaCl, all sodium salts are soluble. And so that will give us a 0.010 molar of Cl minus. All right, and so when it asks for silver chloride, we know that we need the concentration of silver and we need the concentration of the chloride. And so we write the KSP reaction. AgCl solid goes to Ag plus and Cl minus. All right, and when the question is, will you get a precipitate, you know that you're going to compare your KSP to your QSP. If your Q is very, very large, the only way for that to be smaller is to lower the concentrations, which means you have to go to the left and form a precipitate. All right, so we have to compare our Q to the K value. And so initial, this is a solid. That's not part of our equilibrium. Ag plus 0.01. Cl minus also 0.01. And so when we find our QSP, it is the Ag plus times the Cl minus. All right, but Q means it's going to be in an initial state, not equilibrium. If we're doing equilibrium, we're getting a KSP. All right, so we put in our 0.010, we put in our 0.010, and we get 1.0 times 10 to the minus 4. So our QSP is 1.0 times 10 to the minus 4. when you look up the KSP, it is 1.8 times 10 to the minus 10. And so you see that your QSP is much larger than your KSP. All right, and if you put the KSP first and the QSP second and put your inequality sign in between them, that will point you in the direction of the reaction. So the reaction is going left, and you see that on the left we have a solid. That means, yes, you're going to get a precipitate. And so if you add 0.010 molar AgNO3 and 0.010 molar NaCl, you will get a precipitate. All right, now the question is, will it precipitate if we also add 1 molar of NH3? So this is a much more difficult question. Now we have our complex ion formation. And so we have our Ag plus our 2NH3 going to Ag NH3 sub 2 plus. And that has a Kf of 1.7 times 10 to the 7th. And what is nice is they have not changed our concentrations. So we already did this problem. We had, when our NH3 was 1 molar, and our Ag plus was 0.010 molar, and that was 0. We already did this problem. It goes to the right until something on the left is 0. This one was 0. This was the 0.98, and this was the 0.010. And then we solved for x, and we got that our concentration, if you go back and look, our concentration of Ag plus was 6.1 times 10 to the minus 10. All right, so we already calculated the Ag plus for these exact concentrations. They gave us the exact concentrations that they had in the previous problem. All right, so now we have our Ag plus. Now the Cl minus is still 0.01, so we have to find our QSP. So our Ag plus is now 6.1 times 10 to the minus 10. And our Cl minus has not changed. It is the 0.010. So now our QSP is 6.1 times 10 to the minus 12. So now when we compare the two, our KSP to our QSP, all right, K is a constant. It is 1.8 times 10 to the minus 10. Now we have calculated our QSP to be 6.1 times 10 to the minus 12. Now we see that our Q value is smaller than our K value, right? And so the K value is greater than our Q value. So again, if you write the K first, the Q second, the inequality points you in the right direction. All right, so the Q value is too small. In order for that number to get bigger, we need to make more products. It is going to the right. If it's going to the right, that means you're not forming any solid on the left. And so this is no precipitate. All right, so it makes a huge difference when you add NH3 because that forms a complex ion, which removes almost all of the Ag plus. It goes from 0.01 molar to 6.1 times 10 to the minus 10 molar, which then is so small amount of Ag plus in solution that you will not precipitate AgCl. All right. So they go through that. Again, doesn't matter which way you write it, but if you're writing it the way they do, which is the Q value first and the K value second, the inequality doesn't point you in the right direction. All right. So I will always put the K value first, and so my K value, so instead of saying QC is greater than K, I will say that the K value is less than the Q value. And so that means it goes to the left, which forms a precipitate, but it doesn't matter. Here, the Q value is way too big. In order for those numbers to get smaller, they have to react and go make a solid. All right. So, and then again, so they don't recalculate it. It's been found in the previous example that the Ag plus is 6.1 times 10 to the minus 10. You plug that in with your Cl minus, you get your new QSP. I don't know why they're calling it whatever, you can call it QC, but this is specific for solubility products, so I will call it QSP, which is exactly the same as QC. All right, so 6.1 times 10 to the minus 12, and again, that's too small, and so in order to get big, it's got to go to the right to make more of it, and that is aqueous, not a precipitate. All right, so this problem is very difficult. So looks very simple. All right, calculate the molar solubility of AgCl in 1 molar NH3. All right, so whenever you're asking, a question is asked about molar solubility or precipitate, you are talking about a KSP reaction. Anytime you're adding a Lewis base, like NH3, you are talking about a formation of a complex ion. All right, and so you have two reactions going on here. You've got your AgCl solid going to Ag plus and Cl minus. That is your KSP equation. That's the 1.8 times 10 to the minus 10 as the constant for the KSP of AgCl. You also have your Ag plus reacting with the NH3, two of them, to make your complex ion Ag NH3 sub 2 plus, and the Kf value is 1.7 times 10 to the 7. All right, and so you're going to add these two reactions together. When you do, you will notice that the Ag plus is going to cancel. So you end up with AgCl solid and 2 NH3. So here's where you get AgCl in NH3, and you're looking for its solubility. And that gives you your Ag NH3 sub 2 plus and Cl minus. Now you got to find the K value. So when you add two reactions, you have to know you multiply the K values. So this is your KSP times the KF. So you got to take your KSP times your KF. You add reactions, you multiply the K values. So 1.8 times 1.7, that's 3.06. All right, and so your K value here for this reaction is 3.06 times 10 to the minus 3. All right, and so now we go initial and then change and then equilibrium. All right, so a solid is not part of our equilibrium. NH3, it's 1 molar. We didn't add any of our complex ion. We didn't add any of our Cl minus. The reaction has to go to the right. So minus 2, and since it asks for molar solubility, I'm going to use the letter S. X is fine. I'm going to use S because we're finding the molar solubility. And then here is plus S, and here is plus S. So at equilibrium, 1.0 minus 2S, and S, and S. All right, and so when you write your K, it is equal to your Ag NH3 sub 2 plus concentration times your Cl minus concentration divided by your NH3 concentration squared. And then you plug in your numbers. You got your 3.06 times 10 to the minus 3, that's your K value. You have S, so you have S squared, and you have 1 minus 2S quantity squared. All right. You can do this by successive approximations. Neglect your minus 2s, and then you will have to check it. And I believe this one takes S1, S2, S3, S4. You would have to put it in 3 times, and 3 and 4 would give you the same answer. All right, so that can be done. That is not a problem. However, if you look at this, there's an easier way to solve it. We have a perfect square on the right. That's squared, that's squared. So if you recognize this as a perfect square, you can take the square root. If you do not recognize it as a perfect square, you will do successive approximations and get the exact same answer. All right, and so we take our 3.06 times 10 to the minus 3, and we take the square root of that, and we get a 0.055317. All right, again, I'll do the sig figs at the end. I carry them along in my calculator, so I'm going to write a bunch of them down. And that is equal to S over 1 minus 2S. All right, so now I have to multiply both sides by 1 minus 2s. So I got to multiply both sides by 1 minus 2s. Multiply both sides by 1 minus 2s. So 1 minus 2s is gone. All right, and so I get 1 minus, and then times 2 here, 0.1106s. And that is equal to S. So I'm going to add 0.1106s to both sides. I'm going to add 0.1106s to both sides. I'm going to add 0.1106s to both sides. And then I get, this is not 0.055317. Okay. All right, I'm running out of room here. So I have I'll rewrite it. So I have 0.055317. So I'm distributing 1 times that and 2 times that minus 2 times that, which was my 0.1106s, and that was equal to S. All right, and so I have my 0.055317 is equal to 1.1106s when I added my 0.1106s to both sides. And now I divide both sides by 1.1106. So divide both sides by 1.1106. 1.1106. And that is your S value. So 0.055317 divided by 0.11063, and that is 0.050. Yeah. 0.050, right. All right, so the solubility is 0.050 molar. All right, again, if you didn't see that you had a perfect square on both sides, you could do it by successive approximations. I did it that way the first time. And again, that takes 4 successive approximations, and you get the exact same answer, 0.050. So either way will get you the correct answer. And yeah. All right, so again, they're taking the square root of both sides. They're using x instead of s. It doesn't matter. All right, and so they rounded their numbers more than I left all my numbers out there. So when they took the square root, then they multiplied both sides by 1 minus 2x. And that got rid of the 1 minus 2x. And so then they had their x is equal to the 0.065, and then they're going to distribute that 0.065 to the 1 and the minus 2x. And so that is your 0.056 minus your 0.11x. Then you add 0.11x to both sides. All right, they skipped that step. Okay, fine. So they skipped the adding 0.11x to both sides plus 0.11x to both sides. So you get your 1.11x is equal to your 0.056. Then you divide both sides by 1.11 and you get your 0.050 molar. All right, so in this case, if you did round it, you would still get the same number, but barely. This is 0.05045, almost rounds up to the 1. I always leave all the numbers and round my number at the end. All right, but 0.050 molar is your molar solubility of AgCl. All right, so if I wanted to find so now we see that when we had our 1 molar NH3, the solubility was 0.050 molar. Now I want to know the solubility in water for my AgCl and see what happened to my solubility when I changed from water to NH3. All right, so Ag plus and Cl minus. So again, in water, these are zeros, and so it's got to go to the right. You're going to have S, you're going to have S. And so you have your KSP is equal to S squared. So 1.8 times 10 to the minus 10 is equal to S squared. So you simply take the square root of both sides. You get 1.3 times 10 to the minus 5. All right, so you see a huge increase in solubility when you added the NH3. Without the NH3, your solubility is 1.3 times 10 to the minus 5. When we added the NH3, the solubility went up by a factor of about 3,000, 10 to the third. It is much more soluble now. All right, and that is because if you look at the first two reactions, what's happening is as soon as the Ag plus is formed, it is being removed. And so you are pulling the Ag plus, taking out a product, the reaction goes to the right, making it more soluble. And then the last thing in this chapter is this table where we do a qualitative analysis. So you'll be given a bunch of metal unknowns. So it could be any metal in there. First thing you're going to do is add HCl. If you get a precipitate, that means that you have group 1 metals. You need to know those. That's your silver, mercury, and lead. All right, so that's the solid. This side is your solid. And this side is the filtrate, or the aqueous liquid. So you filter it. The solid is collected on the filter paper. The liquid goes through. Then you're going to add H2S in 0.3 molar H3O plus, less than a pH of 1, very acidic. Then you're going to precipitate out group 2. You do not need to know the members of group 2. You just need to know that that is group 2. Then you're going to add NH3 to increase the pH. If anything precipitates, that is group 3. You don't need to know the members of group 3, you just need to know that that is group 3. Then you're going to take that liquid and add carbonate or phosphate. And from chapter 4, all carbonates and phosphates are insoluble. That will get rid of group 4 metals. If you do not get any precipitation, then, and it said you had a metal ion, that means you have potassium or sodium, because all sodium and potassium salts are soluble. So the only metals you need to know are the group 1, but you need to know the steps. You need to know the steps, and so, of course, the first step is group 1, second step is group 2, group 3, group 4, and if nothing precipitates, you have group 5 metals. All right, we will start chapter 18 tomorrow.